Hi, good evening, everyone. Am I audible?
Yes, ma'am.
Yes, ma'am. Good evening.
Okay. Let's wait for 2 minutes for everyone to join, then we'll start. Okay, so I think we can start now. So today is your first session for week 4. Week 4 has mainly 3 things we are going to discuss: relational algebra, relational calculus, and ER diagrams. So in today's session, let me start with relational algebra, and then we'll do TRC, DRC, that is relational calculus part, and I'll try to do some part of ER diagram, but mostly that will be covered in the next session. So I'll just give you an introduction to ER diagrams. Okay, so let me share my screen. I hope you have gone through the lectures once.
Yes,
Yes.
ma'am.
Yeah. Is it visible to you?
Yes,
Yes,
ma'am.
ma'am.
Okay, so before we start, let's make one thing clear first. So since 3 things we are doing: relational algebra, relational calculus, and ER diagrams, right? Or for the moment, let's forget about ER diagrams. Let's say SQL queries. That's what we have done in the past 2 weeks. So all of these 3 things, they are equivalent, right? So they're equivalent in power. That means whatever query I write in SQL, same query I can express in terms of relational algebra or relational calculus. Okay. So all 3 of them have the same power. Now, when we come to relational algebra, we'll see what all operations are there, mostly set operations. Relational calculus will have 2 parts. So one is tuple relational calculus or TRC, one is domain relational calculus or DRC. So these two are very important for exam point of view as well as SQL. Okay. So first we'll start with your relational algebra. So if you have any basic idea about set theory, if you have studied that in math, basic operations like set union, intersection, I think all of you have done that, set difference, these things. These will be very useful here. Okay. So what are the basic operations of relational algebra? 6 basic operations we'll discuss. One is selection operation, one is projection, union, set difference, Cartesian product, and rename operation. These 6 are enough for our syllabus. So what does selection operation do? So we'll discuss all of them one by one, right?
Ma'am, why is the intersection operation not here?
Intersection is not required. I'll show you why. I mean, we do not need that here. But it is one of the set operations that is there.
It can be
We will
derived
use it.
from.
Yeah, it can be derived from set difference only.
Yeah.
Okay. So Intersect is the keyword that I hope you have used in week 2 and 3 when you're covering that set operations part in SQL. That keyword is there. Uh,
Where is this topic relevant in real world?
in real world. So see, most of the times when we're working with relational DBMS, right? So there are more than one tables obviously in your database. So at times it is very rare that in real world you will write queries that will involve just a single table in an RDBMS because all tables are related. So you'll mostly be working with more than one table at a time. So in order to get extract data from more than one table, so there are multiple instances. I'll show you some examples. That is where you will be using set operations. For example, even in a single table also you can use it. For example, if I have a table of students, right, for a school I have a table of students with all student information. Now if I want set of all students who were born before a certain date, right? If I want that, then I can just take the entire set as the first set, and then I can take the second set out of it, that is all students born after set date. So if you take that out, then whatever is left is your answer. So set operations can be used in multiple places. I'll show you some good examples here. But first we'll start with select operation. This is not
Ma'am,
set operation.
ma'am, just a bit. I was wondering why this type of means absurd symbols are there. These are so many day by day. It is growing many.
Which symbols like this one,
Yeah,
selection
this
operator, yeah.
one and or
See,
not
what have we
everywhere.
studied in school? In algebra, when you studied algebra in school, it was symbolic only, right? We used alphabet symbols. That's what there was. It was different than arithmetic, where we use numbers. So that same thing is here in relational algebra also. Here we'll be using symbols. When we go to calculus, relational calculus. So you have done, if you have done calculus in your plus two, then you know that we had differentiation, integration, that thing, right? Here we have different tools for relational calculus. So we'll have a lot of different symbols like for all, there exists, such that. So all of these symbols obviously you have to get familiar with, right? Because these queries are going to be there in your exam.
But ma'am, we don't use this in
Yeah, it is used everywhere.
real,
If you're going for, if you plan on
like
doing a
for
higher
writing.
studies, or if you plan on giving gate, these topics are very important, right?
I
In
got that,
real
but
world,
like
Ma'am,
you are, if you
writing.
want to work as a DBA or if you want to work as a database engineer, then obviously you will be working more with SQL queries, right?
Yeah, yeah,
But these are the
that's what
foundation.
I'm saying.
ma'am, this we will get in the fourth book that was recommended,
Yes, yes, everything is there in code.
but it is so fat.
Okay. Yeah, that's why you can follow along with the slides also if that is easier to follow. Okay, so whatever is covered in the slides is more than enough for exams. All right, let's start. So for select operation, the notation is sigma, right? This is small sigma. So the notation is sigma, and in parentheses we have the relation name. This is relation name. That is the table on which I am doing the selection operation. And what is this row or P here? Let's call it P. So this P is nothing but the predicate. That is the condition for your selection. So when I say that I have that student table, right, and I want to pick all students who have scored, let's say, more than 70 in subject, then this more than 70, this condition is your predicate. So selection operation does not select columns; it selects tuples or rows from a relation.
No,
Right. So selection, always remember, don't confuse it with SQL select statement because SQL select is for columns. So if you want to draw parallel, SQL select statement is going to be parallel with projection operation. Okay, that we will do next. This select operation is selection, and select operation draws out the tuples, not the columns. So tuples or rows. And here this P is going to signify what is the condition. So P is the selection predicate. So I can define it like this. If I write a sigma of R and the predicate is P, then this means that we are going to fetch a set of tuples, a single tuple or a set of tuples T, where this T belongs to the relation R and the predicate is true. That is the predicate, the condition that we are passing is true. So this notation will become even clearer when we do relational calculus. This is calculus notation. Okay. So let's take an easy example to understand select operation. Let's take these two tables. Uh, yeah, this one first. Okay, now in this table, how many attributes we have? 4 attributes A, B, C, D. So what is our
Ma'am, why
selection
it is called
operation?
relational calculus?
Because it is calculus that we are using to fetch data from and extract data from relations. Relation means table, right? All of these are based
That is
on
fine, but there is no calculus there, like the
no,
calculus
no.
that we did.
This is not mathematical calculus. This is relational calculus. Okay, you cannot draw a parallel with the calculus that you did in maths. This is different. Okay, this will mostly be, this is predicate logic. Okay, I'll show you predicate logic first, so you understand that, then you'll understand what is this relational calculus. But this is relational algebra currently we are doing. So since I said that relational algebra, calculus, all of these are equivalent in power. That means whatever I can express in terms of relational algebra, I can also express in terms of relational calculus. So that's the thing that you can see here. But for now, we'll just focus on the algebra part. So this is a relational algebra query, right? So sigma is the operator. You're working on relation R. Let's call this relation R. What is the condition or the predicate, selection predicate? That column A values have to be equal to column B values. This is AND operator. And column D value must be greater than 5. So in whichever rows this predicate is true, we will select those rows. So now let's look in the table. So A, B, C, D, 4 columns we have. In first column, is A value equal to B value?
Yes.
Yes. Is D value greater than 5?
Yes.
Yes.
So first column will be part of my result. This will be selected by the selection operation. Second column will not be selected because A value is not equal to B value. Third column, A, B values are equal, but D value is not greater than 5.
Less than
Since
5.
this is, yes. So since this is AND operation, so both conditions have to satisfy, right? So row 3 is also not selected. Second, third rows eliminated. Fourth row, A value equals to B value and D is greater than 5. So fourth row will be selected. So only row 1 and row 4 are selected, and that is there in your result. So this is the resultant table that you will get. Okay, this is very basic selection operation. Another example that you can have is, let's say I have an instructor table. Now, from the instructor table, I want to fetch those rows where the department name is physics. That means where the instructor teaches in physics department. So only those rows will be selected. That is one more example. Now, projection is the actual operation that correlates with our select clause in SQL, right? Because in SQL select clause, what do we write after the select statement? What does it signify? Whatever we write after select, what does it signify?
The
Attributes for what? Where will I see those attributes?
On table
So
header
those are the attributes you
from
want in your resultant query, right? After you run your query, those are the attributes you want in your result. So that same thing is happening here. Projection operation, the notation is pi. Okay, selection is sigma, projection is pi. Same thing based on a relation you're doing. So the relation name is required and the subscript will be, previously what was the subscript? The predicate condition, like department is physics, or the example that we just took, A equals to B and D greater than 5. That predicate was there. Now what is there? Since we can only select attributes here, so the attribute names will be the predicate here in the subscript, right? So notation is this, where A1, A2 are attribute names and R is relation. So A1, A2 are the attributes that belong to this relation R. Result is defined as the relation of k columns obtained by erasing the columns that are not listed. For example, here I have this table, ABC, all of these values. Now, if I want just A and C, okay, so what will be my relational algebra notation? Pi
A, C.
of R, here A, C, correct. So this, now why is it not having 4 rows? Because projection operation inherently gets rid of all the duplicates. No duplicates are allowed. So since this first 2 rows are duplicates, right? Alpha 1, the AC combination are duplicates. When you take them out, so in the original table, these are all unique tuples, you can see, right? The ABC combination is unique for every row. But when I take just A and C out, then there are duplicate combinations I can find, alpha 1. So only one of them will be retained like this. This is a very good property of projection operation, that it always gets rid of all duplicates. Right, this is very important also. So I'll just write it down on the slide.
Ma'am, so we need not give any predicate for projection, right?
No, see, projection is not working on any condition. It is just asking that what columns do you want me to fetch. So only the column names. Selection
Ma'am,
is the one where you do the condition.
ma'am,
Ma'am, but we can provide predicates also if we want.
No, in projection we cannot provide predicates. Predicate, that is condition, is only for selection. Okay, usually when we want to, let's say, if I want to replicate an SQL query using relational algebra, then I'll be using a combination of projection and selection operations. Okay.
Ma'am, here if I write just the projection operator and A comma C and a blank, I mean open
Then
parenthesis.
it will do nothing because there is no relation to fetch it from.
But it is the same thing I'm asking for. What is the relation between them? Oh,
Relation is not relationship. R is the table name.
oh, acha. I
Right?
see.
Like this. This is projection operation performed on instructor relation or instructor table. And what am I fetching from that table? The columns ID, name, and salary. Okay. And duplicate rows are always going to be removed from the results. So relations, why this is true, that why does it remove those duplicates? Because the relations are always sets, right? So you have done Python, you know what is the characteristic of a set? There are no duplicates. Same thing applies here. Relations are always sets. That means in an ideal relation, no two tuples will be exactly similar. That's why we have the concept of primary key, which is always unique, right? So no two tuples are exactly similar. So when we do this projection operation, sometimes we can fetch columns which might have duplicate combinations because some other column is missing. For example, here, if the B column was there, then these two rows are unique rows. But as soon as I take the B column out, A and C combinations become duplicate. So it has to inherently remove that. So selection and projection, is it clear for everyone? Any doubt?
No, ma'am.
No, ma'am.
Now, this is very important, union operation. Okay. So what is arity of a relation? This
Like
term
both have
arity.
same number of.
No. Don't read from here. I'm just asking what is arity. What does the term arity mean in terms of DBMS?
If there are two columns in in the table R, then there should be.
It's not like that. Okay, it's not some condition or something. It's a property of a table. What is arity? So arity is your number of attributes in a table, right? Like this table R, it has arity of two attributes A and B. Similarly, S also has arity of 2. So whatever is the number of attributes present in your table, that's your arity. Okay. So union operation, you all know the notation, this R union S. So I have two relations R and S. When is it possible to perform a union? So this is not so easy, right? In maths, we learned that if I have two sets, I can always perform a union between them. This is not so easy because here now what matters is the domain and the arity. So I have two tables R and S. I can only perform a union between them because they have the same arity, that is same number of attributes in both of them. If one of them had 2 attributes, one of them had 3 attributes, then it is not union compatible. Okay, so there are these rules in union compatibility that you have to follow. Okay, so this rule also applies in other set operations. So first, let's deal with union first. So yeah, what did I say? That union compatibility means that R and S, if I want to perform union between these two relations, they must have the same arity, that is same number of attributes. Second thing is what? The attribute domains must be compatible. Example, if second column of R, that means what is second column of R? B. So this column, what is the domain? Can I say integer? Yeah, integer. Okay. So second column of R deals with the same type of values as second column of S. So B here and B here, both of them have the same domain. Only that's why we can perform a union. If this was ABC, then there will be no union because domain is different. Okay, so two things: arity, domain compatibility. That means corresponding columns from both tables should have the same domain.
Ma'am, a question, ma'am. Suppose in the parent table I had some 5 rows, and out of that I selected 2 rows, and in another table there are 3 rows. I selected 2 rows. They are compatible. Can we do an union on them, or we cannot?
Yeah, sure, because now you're creating the sets, right? So first you selected 2 rows from the you selected 2 attributes from the table that had 5 attributes. So your selected set only has 2 attributes, right? Again, you selected 2 attributes out of 3 attributes. So now your second selected set also has 2 attributes. So both have the same arity. These are both sets you created. As long as they have the same domains also for corresponding attributes, you can always perform a union. Okay, but you cannot perform union between the parent tables with 5 and 3 attributes. That's not possible.
Ma'am, if we have names as A, B, and in the relation of S, we have column names as C and D, then can we perform?
No. Column names are usually you will see that column names are same only. Okay, in case of union.
Ma'am,
So-
in case they are say not if they are not same, can we rename them to be same?
Yeah, you can rename, sure, but usually we don't do that. I mean, usually we want to perform a union in case of real world problems. For example, we have this one question that we have a relation, that is section table. So there we have all of this information about where in which semester a student is taking a certain course, in which year. So we want to perform some operation that has some meaningful data, right? That gives us some meaningful data. So if you just rename two random columns and you're doing a union, so your result might not be very meaningful, even though they have the same domains. They might be representing something totally different. For example, a student's marks and an instructor's salary. These two are both in having what? Numeric columns, right? So the domain is basically same, but doing a union on them will not give you any meaningful data, right? So usually this type of operations are performed on the same table mainly. Not always, but mostly you will see those as the examples. So to find all courses taught in, for example, take this one, to find all courses taught in the fall 2009 semester or in the spring 2010 semester. This is our question. We want a result where we want all the courses that were taught in either fall 2009 or spring 2010 or both. That means there is one set for fall 2009 and there is one set for spring 2010, right? We want all courses here, and if there is some sort of an intersection, then we want that too, right? So this falls under union. This is the definition of union, that two sets like this
Yes, ma'am.
is the universal set. This is your union.
Yeah.
Okay, so how to represent that in terms of relational algebra? First, see, I have the section table. So what are the things that I'm interested in? What are my predicates? That I know the semester must be fall and the year must be 2009. So sigma, which tuples am I choosing? Where the semester is fall and the year is 2009. So that's your predicate. So now we have done the selection operation, which has now given us all the desired tuples or rows. But what do I need? I need only the course ID. See, to find all courses, that's all I need. So I will just extract the course ID column from there, right? So course ID projection over this. So usually that's what I said, that when we want to perform these relational algebra operations, mostly it will be a combination of selection projection, right? And again, so this is your course IDs that were taught in fall 2009, this set. Same do it for spring 2010, which is this set. The semester is spring, year is 2010. First you gathered all of your desired rows or tuples, and then you extract just the course ID column from there. So now, how many columns do I have in each set? In the first set also I have a course ID column. Second set
Ma'am,
also I have a course ID column.
can you repeat this part once again?
Which
What is
part?
course ID here? The last
Course
row.
ID is a column, is an attribute in the section table. Okay. Let's say the section table looks like this. This is section table. It has attributes like this: semester, year, course ID. Like course ID 101 was taught in fall semester of year 2009. This is one tuple. Okay. So when I write that from section table, select the tuples where semester is fall, year is 2009. So this tuple will be selected because the predicate condition matches. Now from here, what data do I need? I just need the course ID because it's given in the question. Find all courses, nothing else. So I will extract this column only, course ID. So for that you write projection of course ID on this data. Understood?
Okay. So we are projecting the course ID.
First you do selection.
column.
First you do selection, then you do projection. First, this inside the parenthesis, this part will get executed. Then only you can project from it, right?
Okay.
So first selection, then projection. This is usually how it works. Now, both of these sets that you have created, one for fall 2009, one for spring 2010. What is the arity of each of the sets? How many columns are there in each of the sets?
2.
One column.
Only one column I have projected, course ID.
Course ID.
Right. So arity is 1. That means do both if I treat them as separate relations, do both of them have the same arity? Yes.
Yes, ma'am.
Yes, ma'am.
Are they
Yes,
domain
ma'am.
compatible?
Yes, ma'am.
Yes, ma'am.
So both conditions are satisfied. That means these two sets are union
Ma'am, a
compatible.
small confirmation. Domain compatible means the same data type, right?
Same data type. Yes.
Okay.
Ma'am, do they have to have the same data type and the same column name as well? Or just the same data
column,
type?
same data type is the main thing that is written in the rule, but usually they have the same name also.
Got it.
Since see, these are both coming from the same table, so obviously they will have the same name. Okay. Now these two conditions are satisfied, so we can definitely tell they're union compatible. So now you can perform your union operation. So first, to understand how this union operation works is first the selection will happen in both sets, then the projection will happen, then we will check it is domain compatible, it is same arity, it is union compatible, then we will perform union operation. So a lot of steps are involved. So is union operation clear for everyone?
Yes.
Okay.
Yes,
Now
ma'am.
let's do
Ma'am,
it
just
from these
wanted
two
to
tables.
confirm.
Yeah.
Duplicates will be removed, right, ma'am? Just wanted to confirm.
This is something, okay, let me come back to this because I have to discuss one more thing regarding this. Okay, let me just do this union in this example, then I'll answer your question about duplicates. See, this relation and this relation, R and S. Okay, if I want to perform a union, is it possible to perform union between these two?
Yes, ma'am.
Yes.
Right.
Yes, ma'am.
So if I perform union, that means I will have everything from both tables, right? So I should have all combinations. I should have alpha 1, alpha 2, beta 1. Here, one more alpha 2 is there, and then beta 3. Right? Just give me a second. Yeah. Okay. So in the result, I can see that here I had 5 combinations, but in the result, I can see only 4 combinations. Why? Which one was removed?
Duplicates are removed. Alpha 2.
Duplicates are removed.
Alpha 2.
One alpha 2.
This.
Alpha 2.
Alpha 2. So this is present twice, once in table S, once in table R. So only once it will be calculated in the result, right? So that means what? Union operation is by default going to remove all duplicates. But there is one more operation called union all. Okay. Union all is the same thing as union. It will take all the same union compatibility rules, but the only difference is it will retain the duplicates. So if I write in SQL, if you write union all, and that's how you join two tables or do union of two tables, then it will retain all duplicate rows also. Okay, so union will not retain duplicates. I'll write it down, union, no duplicates. But if you do union all, then there will be retain duplicates. In that case, all 5 combinations will be there. Okay, so there is again same thing with except clause. Except
Like
clause.
we have a notation for union. Is there any notation for
No,
union?
in union all we use it just in SQL, not in relational algebra.
Ma'am, one clarification, please. Can you please tell me what is the difference between union and union all?
Yes, see, in union, we saw in this example that union should ideally take everything from set 1 and everything from set 2. So there were 3 combinations in set 1, 2 combinations in set 2. So overall, the union result should have 5 combinations, right? But here we only have 4. Why? Because the alpha 2 combination occurs twice. So that duplicate is removed. So union inherently removes all duplicates. But there is another operation called union all, which will retain these duplicates. It will not remove. So if you used union all, in this case, there will be 5 rows, one more row for this other alpha 2.
Thank you.
Okay, that's the difference. So that's your union. Now this is difference. So difference, everyone, again, you all know that it is set difference means if I have a universal set like this is my set. Is someone asking anything?
Can you just a little bit repeat what you said? Union or
See, union and union all basic differences. Union does not retain any duplicates when you perform union between two tables. All duplicate combinations are removed. But union all will retain the duplicates. Okay. See, if I have two sets like this, set A, set B. So if I do A minus B, that means I want everything in A that is not present in B.
Only, yeah.
So I will take this part out. And this remaining part is my answer. Right? Similarly for B minus A, just take the intersection and the rest of A out. So this is your basic set difference operation. Same thing we can write in terms of tuple relational calculus also. I'm not going to do this right now so that you don't get confused.
Ma'am,
So,
is this set difference equal to that right join or left join?
No, join is different. This is not same as join. This is same as except operation. In SQL, when you do except clause, that's this.
Okay. And right join, left join is which then?
That is a completely different operation, and that is falls under joins. Different types of joins are there. That has nothing to do with this. Okay. So set differences must be taken between again compatible relations. That means again same thing like you had union compatibility rules. You also have set difference compatibility. That means both sets that you are performing this difference between, they should have the same arity, same number of attributes, and domain compatibility, same rules. So here I have in R set, I have A and B, S set, I have A and B. So these are definitely arity is compatible. And I can also check the domains of corresponding attributes are same. So this is set difference compatible. Now, if I do a difference between these two, if I do R minus S, what all combinations should be taken out from R? Just the matching ones, that
Alpha
is
2.
alpha 2. So only alpha 2 will be taken out. Nothing else is in common. So resulting is alpha 1, beta 1. Now, same thing if I want to write in terms of relational algebra. So, for example, if I say that I want to find all course IDs that were taught in fall 2009, but not in spring 2010. So, again, if this is the fall 2009 set and this is the spring 2010 set, right? So, there are some intersections. So, I want what? Fall 2009, but not spring 2010. So, I will take out this part. Only this part is my result. So again, let's do the same thing. Let's create the two sets. First, let's create the fall 2009 set. So from section table, select those rows where semester is fall, year is 2009. This is your first set, from which I will now select the attribute I need to project, which is course ID. First set is done. Second set is again from section table, select those rows where semester is spring and year is 2010 and project all the course IDs. So this is all course IDs from fall 2009, all course IDs from spring 2010. To do a difference, that is take out all IDs from second set from the first set, then you will be left with all course IDs that are taught in just fall 2009, not in spring 2010. Like, difference is clear for everyone?
Ma'am, I had a question here. There was one type of question in the non-graded sets that you had one clause like projection course ID this minus course ID this, and again another except treatment. So what will it return and why?
I did not understand. What is it
Either
like?
you look at this thing, you keep the first line same, okay,
Hmm.
and then you put the minus sign and keep the second line same and make a third line, which is you put a minus again and do the second line repetition. So what will be the answer and why?
Like if I do a minus here.
Yes, and the same thing of this second line, you just copy and paste. So now they were asking the answer of that in one of the non-competitor. How would I proceed for that?
So does anyone know what this expression is? Something like this.
Intersection.
Intersection, ma'am.
Right? Intersection. So that's what it is. See, very easy to spot. Here if you have set A and set B. First take out set B from set A. What is remaining? This part. Correct?
Yes.
Okay. Now, if I want to get intersection, it is actually, I think we wrote it a little wrong.
R minus S.
Yeah.
Yeah.
Or S minus R
S
minus S.
minus R
No,
minus.
but the question is R minus S minus S. So what will I do? It is not R minus R.
Can you show me the question once?
It is somewhere in the graded, non-graded assignment.
Somewhere in the activity questions, one of the question, ma'am. It was.
Okay. I'll check that question. You just send, if it's possible right now, just send me the question number in the chat. I'll check it out. But if it is S minus R minus S, then it is an intersection. Okay. If it is different, then I'll check that question and tell you. It might be meaning something different in that context of that question. I have to see that. Okay. So difference, and this is your intersection. So intersection, see this one. This is what I was talking about. R minus S. This.
Ma'am, if we want the other formula could be S minus of S minus R, right? Right. Yeah.
Okay, so this is the intersection operation. Again, everyone knows set intersection. If I have two sets A, B, this is my intersection. That is common point of intersection between two sets. So same rules apply. Intersection also you have to check the compatibility of both sets or both tables and the domain compatibility also. Okay, so here if I do intersection of R and S which are compatible, then I'll get only alpha 2, only common combination. Right, but intersection we won't be using a lot as much as union. It will be there, but mostly since it can be used just by using set difference, so we'll mostly be using difference. Now this last, this one, Cartesian product one, this is very important other than division operations. That will take some time to discuss. So Cartesian product is the basis of all joins that we will be doing from now on, right? So Cartesian product means what? If I have two tables, one table has m combination, and one table, let's say table A has m rows and table B has n rows. If I perform a cross join or a Cartesian product between them, then resultant table will have how many rows?
M cross N.
M cross n rows.
M cross N.
It means all possible combinations.
We have duplicates, what will happen?
Everything will be there. Okay, whatever is there in both tables, all possible combinations. Now this is the basis for all joins that we'll perform next. So this is the first basic type of join. Cartesian product is also known as cross join. So notation is just this cross R cross S. So here I have this table R, this table S. So how many rows will be there in R cross S? 2 rows here, 4 rows here. So 4 cross 2, 8 rows in the resultant table. One more thing is that now let's say if instead of C, D, E, here I had B again. What will happen?
We have to rename actually.
Yeah, so in that case I can write R dot B here and S dot B here. Right, so this B is coming from R table, this B is coming from S table. That's why in SQL when you do such type of joins where there are similar named attributes, right, same name attributes, then you have to also prefix it with the table name itself so that you don't get confused. Okay, now assume that
So, R cross S and S cross R will
Same
be different. Will be different, no?
Different means number of this thing will be same, right? Rows and combinations are also same.
But relation is different.
How is it different? See, if I do S cross R, it will just look like this: C, D, E, A, B. But are the tuples anything different? It will still be this alpha 10 A from this first
Yeah.
row and the first row here alpha 1. Same
So,
thing. The
so
tuple
the
doesn't change.
if the order of attributes remains same,
Order of attributes don't matter in a relation. Okay. Order can be anything. The tuple itself should be unique.
yeah, okay.
Okay.
Ma'am, so
assume-
here
Could
we
you
can.
please repeat this renaming part?
Yeah, see, I was saying that if in case you are trying to join two relations where there are attributes with the same name. So like here I have B, if I here also I have a B attribute. In that case, in SQL when we do it, then we write the relation name as a prefix like R dot B to signify that this B attribute is coming from R table and S dot B, this B is coming from S table. Right, so here when in the resultant we will write A, R dot B, S dot B, D E like this. Okay.
Ma'am, so in this Cartesian product, we can say that R cross S equal to S cross R.
Same thing, yes. Order does not matter here. Okay. No matter in which order you do, the combinations will be same. Now, one more thing I wanted to discuss. One second. Okay, so assume that attributes of this relation R and relation S are disjoint. Disjoint means that the attributes do not have anything in common. They're mutually exclusive. That is, the intersection of set of attributes is null. That is in this case, AB and CDE. They don't have anything in common. If they're not disjoint, then renaming must be used like this. Okay.
Ma'am, what is being represented by the capital R and
Set of attributes of relation R and set of attributes of relation S.
So
Okay.
if they have common attributes, we have to just rename those attributes.
Yeah.
And
In the resultant
got
table, you will rename it.
Got it.
Okay. Is cross product clear for everyone?
And in the final table,
Hmm.
hello. And in the final table, if what we will have two columns for B, then like if renaming is done.
Yeah, that's what I'm saying. In final table, then it will look like this R dot B. And if this is also B, then it will be S dot B. This is coming from R table, this is coming from S table.
Okay. Yeah. Got it.
Ma'am, how can we read that defined as R cross S is equal to T Q?
This thing is calculus, relational calculus. I'm not doing this right now because you don't know the notations. Okay. This you can do it yourself once I teach you TRC, DRC. Then you will be able to make sense of this. Okay, this is nothing but this means that T and Q are what? These are the set of tuples that are coming from relation R and relation S. So all possible combinations of those. So TQ such that T belongs to relation R, Q belongs to relation S. Yeah. What are you asking?
Tuple relational calculus, I couldn't understand how to do the problems. Will we cover it in the session?
Yes, I will take examples. Okay, that's why I'm trying to move a bit fast because there's a lot to cover.
Got it, ma'am. Got it.
Okay. So I hope this is clear for everyone. Cross join is the easiest join you will do. Now, rename operation, this is represented by row, this alphabet row. Right now, this allows us to rename basically. So it will let us rename some relation. For example, if I want to rename this relation E to X, in that case, you will just write row of E and the name that you want to change it to, write it as a subscript. So subscript X. That means now the relation is renamed to X. So if relational algebra operation has relational algebra expression E has arity n, in that case X will also have arity n. That means same number of columns are there. Columns are not disturbed, right? Everything else is same in the table, just the table name has changed from E to X. So now the same result of the expression that was coming under E will now come under the name of X. Okay, but attributes remain same. That's your rename operation. Now this one will take some time to understand because this is very important for exam. So this is.
Ma'am, why do we divide like this? This is an abnormal division.
No, it's not. Okay, I'll show you how division works in this relational algebra and why we need it. So division operator is applied to obviously two relations. At one time you can divide two relations, apply division operations between two relations. So this whole thing that is given here, we will decode this, right? But before that, let's understand how to do division just by looking at the tables. Okay, so for example, take this. If I have table R and table S like this, and this is my resultant table, R divides S, R divided by S. Okay. Now, look clearly. In R, how many attributes do I have? In R table?
Two.
Attributes, not rows. Attributes.
Two.
Two. S, I have only one attribute. Now, in R table, can you spot any attribute which has the same domain as S attribute?
Green and
Yeah.
Just tell me in R table, which is the column which is having same domain as the subject column in S table?
Module and
Module.
Module. So I can say that module and subject are having the same domain.
Right.
Okay. So now our job is to see that what is the other attribute in R? Lecturer. We have to see that which lecturer teaches, let me put it this way. Which lecturer corresponds to all the values of the subject column in S table? So since subject column here has only one value, okay. So you have to check which lecturer teaches or has a corresponding combination with this particular subject. So Green teaches prologue, that is one combination, and Lewis teaches prologue, that is another combination. Okay, now in here, if I change it like this, in subject, if I also have databases, in that case, now you have to find out which lecturer teaches both these subjects. So what will be the answer now?
Green and
Only green. Only green. No one else teaches both, right? Lewis teaches prologue, but not databases. Brown teaches databases, but not prologue. Smith teaches databases, but not prologue. So the attribute in R table should correspond to every single value of the attribute in S table. This is division. Let's take one more better example. Let's take this.
Ma'am, this is just a projection and selection operation.
Yes, it is a combination of just selection, projection, nothing else. Okay, so this example will make it much clearer. See, here I have S number, P number in table A, and in table B1 I have P number, only P number, and there is only one value under it. So now if I do A divided by B1, what does it mean? You have to choose first, see what is the common attribute between these two, P number. What is the other attribute in A table? S number. So which S numbers correspond to every single value of P number in table B1? So in table B1, how many P numbers are there? Only one, P2. So find out which S numbers have corresponding P number as P2.
S1, S2, S3, S4.
S1, S2, S3, S4. So that is your answer. In B2 table, now if I do A divided by B2, now you have two P numbers, P2 and P4. So which serial numbers are corresponding to both P2, P4? S1 corresponds to P2. S1 corresponds to P4. So S1 is 1 of our results. S2 corresponds to P1, P2, but no P4. S3, only P2. S4, both P2, P4. So S4 will be selected. So S1 and S4. Similarly, do it for A divided by B3. Tell me the result. Which serial number will be selected?
P1, P2, S1.
Only S1 has P1, P2, and P4.
Correct. This is very easy to also determine. Why? Because for all the other S numbers, you can see that there are at most two rows. So no way they can have 3 combinations, right?
Ma'am, if there is no such scenario, then
Then the result will be null.
okay.
Okay.
So whichever has every instances of the p number in the s number, we will
Yeah,
select that.
basically we have 2 tables, right? The divisor table and the dividend table. So A is the dividend, B is the divisor. So we will check that what is the common attribute between these 2 tables. Based on that, the division is occurring. Now, the other attribute that is present in the dividend table, here A. So we have to check that which of the dividend table values have all possible combinations with the divisor table values. Only
Ma'am,
those will be selected.
excuse me, ma'am.
Yeah.
Ma'am, for B2, if I divide A by B2, P2, sorry, P2, S2 should also come.
So S2 has combinations with both P2, P4. It has with P2, but where is the combination with P4?
Okay, oh, so we should have
Yeah,
combination.
corresponding combinations with all possible values.
Okay.
See, take one more example. This will make it even clearer. This
And
example.
if there were 3 attributes in the main table,
No, no. Division is based on this. 2 attributes we will do. Okay. 3 attributes, no. We'll only work with 2 attributes in the dividend table. See this expression that we saw. This one. So here, yeah, you can have. Okay, you can have more than 2. Obviously, that is in a table. You definitely can have more.
Sorry to interrupt, ma'am, but in the lecture videos, the professor stated that whatever columns are not in the thing
Whatever
that we're
columns are
dividing
not,
by,
yes.
we
Whatever
ignore
columns
that
are
and
not
everything
the,
else we write.
right. So whatever columns are not common in both, right? Whatever columns are not common in both. So we have to consider all of them. So why am I saying that you just work with 2? Because those are the questions that you will face. In your assignments also you can check. So the division operator questions, we usually use 2 of them only. So not to confuse you. That's why. Because you have to take care of combinations, right? So whenever there are multiple columns, there's possibility for multiple combinations also. Then the check becomes even difficult, because first of all you will have to keep track of combinations in the unique columns, that is the non-duplicate columns, right? There are common columns between 2 tables, and then there are columns which are not in common in the dividend table. So if there are more than one such non-common columns in dividend table, then there is possibility for more than one type of combination. Like here only I have S number. If I had in this one, if I had instead of S number, I had one more, let's say R number, then there is one more attribute now. So there is a possibility of one more combination change. So like here now I'll have R1S1, I might have R2S1, like this. Okay, so to not make it complicated, we use just 2 columns in the dividend table in the questions also, but there can obviously be more. Okay, we always work with a set of attributes. So in the actual division operator relational algebra expression that you can see here, this one, see here we are mentioning set of attributes. We are not mentioning individual attributes. So there is possibility to have more than one. All right. But see, all the examples we are trying to use only 2, because this is confusing as it is. A lot of people get these questions wrong. So we are not complicating this too much. In gate questions also, mainly you will see that wherever division operator has come, it is based on mainly 2 attributes in the dividend table.
Ma'am, for examination purpose, there'll only be 2, no, ma'am? Just
Yes,
wanted to confirm.
yes. Mostly I'll have only 2, and you can check the PYQs also. Okay. So yeah, this one, tell me now. B has 1 and 2. So which of the A values correspond to both these combinations?
Alpha and
Alpha.
beta.
The beta corresponds to 1. Beta also corresponds to 2. Right?
Finish.
Anything else? No. That's it. So that's your answer. Now let's do this one, since you wanted one more with more attributes, right? So here we have 2 attributes in common, D and E, and 2 attributes here also in the S table. So now we have to check for a combination. Like I said, now the combinations increase. See, earlier we just had to check for, if I had just D, I had to check for AB. Now you have to check for A1, B1. There might be A2, B2, like this. The number of combinations increase, that's why the complexity will increase. But this is easy to do. So what are the other three attributes A, B, C? These will be in your division result. Okay. So let's see which ABC combinations have corresponding A1 and B1, both combinations. So
First row.
alpha A alpha has A1. Does alpha A alpha have B1 also somewhere?
No.
No. So this is not there. Alpha A gamma has A1, but alpha A gamma also has B1. So this is part of our result. See, alpha A gamma is one of the tuples in the result. Now beta A gamma has A1, but beta A gamma has B3, not B1. So this is not part of it. Gamma A alpha has A1, gamma A alpha has B1. So that is part of your result.
Gamma, no ma'am, gamma A then gamma.
This gamma A beta, this has only B1, no A1. Okay. So these two work similar only, but mostly in the exam you will see that there will be two attributes. Okay. Because there is already less time in exam, no need to confuse you more. Now let's quickly discuss this expression, because we are studying relational algebra, we need to understand how this corresponds to the same thing, right? Can you see the blank PDF?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay. Now I will take an example and we'll solve it together. So division operation we are doing. This just looks like a big expression. Okay. Once we break it down, it is very simple. So let's take two tables, student table and course table. So in student table, let me have two attributes, SID and CID. And in course table, I only have CID. So let me write some combinations, S1, C1, S2, C2, S3, C1, S1, C2, and S2, C1. Let me have these five combinations, and in CID I have C1 and C2. Okay, these are my two relations. Now if I just do a normal division, so if I do student divided by course table, you tell me what will I get in result? What will be the attribute I'll get in result?
S1, ma'am.
S1 and S2.
SID is the attribute name that will be in the result. Now which values of SID will be there?
S1 and
S1,
S2.
S2.
S1 corresponds
S1,
to
S2.
both C1, C2. So S1, S2 corresponds to both C1, C2. So S2, S3 is not there. Right? This is what we learned till now. Now how can I do the same thing using the relational algebra operation or expression that we saw? So let's write the expression first. This division operator is same as writing pi of x minus y of r minus pi of x minus y. See, here they used r minus s, right? And I am using x and y. So this I am doing to avoid confusion, since here what is happening, this r, small s, these are what? These are the table names. And this capital R, capital S are the set of attributes of those tables. So capital R means set of attributes of table R. Capital S is set of attributes of table small s. So instead of doing this rs repeatedly, let's take s, x, y. Okay. So x minus y of table R, pi x minus y of all the other parts of the expression are same. Pi x minus
Ma'am,
y.
can you please explain what is X and Y?
I will write it down. Just one second. So this is the entire expression that we have. Right, this is division operation in relational algebra. Now R is our student table, S is our course table, X is set of attributes of R, that is student table. So what are the attributes of R? SID, CID. Y is set of attributes of S, that is just CID.
Yeah.
This is clear?
Yes,
Now
ma'am.
we will break down this into three constituent parts. Okay, first we will solve for this part. What does this part mean? R table is my student table. Now X minus Y. First tell me, we decoded X is what? SID and CID.
NCID.
Y is Just CID.
CND.
So if I do X minus Y, what am I left with?
Student IDs.
Only SID. Okay. Now this is what I am extracting. So X minus Y, if it is CID, equivalent to CID, where am I taking it from? The student table or R table. That means this expression will lead to what?
S1, S2, S3, and S1, S2. The entire
This expression will lead to EID from R table. Now, what are the course IDs in R table? I'm sorry, SID, not
SID,
CID.
right, ma'am? Yeah.
SID.
Ma'am, we learned subtraction with relations, but how are you subtracting to
This is normal
attributes?
subtraction. This is normal subtraction. This is not set difference. Okay. This is just normal subtraction. That okay. If you want to
Ma'am,
think of
how
it
is this subtraction working?
this is okay. Let's talk about set difference. What is X? Set of attributes of R. So this is one set that contains SID and CID. And Y is what? Set of attributes of S. What is that set containing? Just CID.
Got it, ma'am, got it.
So there is, we can perform an operation between two sets, right?
Yeah.
So if I take out this second set from the first set, then what element is left in first set? SID.
SID only.
So that SID only I am projecting. From which table? R, which is student table. Now tell me, in student table, how many distinct SIDs are there?
S1,
S1, S2,
S1, S2, S3. Because projection will remove the duplicates, correct? So I will have S1, S2, S3. First part of expression is done. Now let's do the second part. So let's do the inner, this part first. This is same as this, right? Phi of X minus Y of R. This is same as what we just did, correct?
Yeah.
That is this expression. And what is S? The entire S table, which is nothing but CID, C1, C2.
Yes,
and I'm
ma'am.
doing a cross join between them or Cartesian product. That means I will be getting all possible combinations. Now, how many rows are there in this and how many rows are there in this?
3 and 2, ma'am.
Cross 2. 6.
That means now if I do the, so let's write the combinations then. This will have SID and CID as the resultant attributes. So I'll just write it here so we can write the combinations while looking at it. First combination is S1, C1.
S1,
Then
C1,
S1,
S1, C2,
S2, C1,
C1, S2, C2,
C2,
S3, C1, S3, C2.
S3, C1 and S3, C2. Correct.
Ma'am, it is Cartesian product only?
Cartesian product, yes. Yes, cross sign. So now this part of the problem is solved, just this part. But we have a difference with this. What is this? So tell me first, what is X minus Y? SID.
SID.
What is Y itself?
CID.
CID. That means I want to extract SID and CID from where? Relation student. So if I extract SID and CID from relation student, that means I am taking the entire table student only.
Yes.
Right? And student table combinations are already here. Let me still write that down again. So this part evaluates to this, and now this third part evaluates to this student table itself. Nothing has changed. So student table has combinations S1, C1, S2.
Ma'am, could you once again explain how did you get a student table? Like, why are you writing down student table? That logic?
Look, what is here? I am projecting what from student table. What am I projecting? X minus Y. What is X minus Y? SID.
SID.
And again, I have comma Y. That means I am projecting two attributes. So what is Y itself? CID. So I'm projecting both SID and CID from student table. That is the whole student table itself. It only has two attributes.
Okay, got it. Okay, that's a comma. Like we are
that's a comma.
We are selecting both of them. Okay,
Yes,
got it.
like A1.
Yes,
like,
understood. Yes.
Okay. So now let's write down student table here.
Explain the middle one once again.
I will. Let me write down the student table once. S3, C1. S1 C2 and we had S2 C1. So this is student table. Okay, now see the middle one, what happened? This part, pi of x minus y r. This is same as this first expression,
Yes, ma'am.
right? I am doing a cross join of it with table S, that is course table, that is this one. So cross join of these two will give me 6 rows, right? 3 rows here, 2 rows
Yes,
here.
ma'am.
So those 6 rows, that is all possible combinations I have written here. Understood? But see now, there is a difference operation. Between whom? Between this and this.
Ma'am, in the middle term, there's a projection x minus y again, right? After the product.
This one, this outside.
Yeah.
This projection is on the whole thing. That is the result
Oh,
of
okay,
the
okay.
subtraction. Okay. So let's do the difference first. So now I have the first set, I have the second set. So I have to subtract second set from first set. So what are the common combinations? This is set, let me call it, this is set S1, this is set S2. So I'm doing S1 minus S2. So take out all the common combinations that are there in S2 from S1. So is S1 C1 present in this?
Yeah, first.
Yes.
That is gone. S2 C2 gone.
Yes.
S3 C1,
Yes.
S1 C2,
Yes.
S2 C1. What am I left with?
Yes.
S3 C2.
S3C2.
Now this is the result of this inner part of the parenthesis. This whole thing evaluates to S3 C2. From this, what am I projecting? Again, phi of x minus y gives what? SID.
SID.
So just project the SID from here. That means what will be projected? S3.
S3.
So SID, S3 is projected. Now do the subtraction here, this subtraction. So that is subtract. Now this is your set 1, this is your set 2. So if I take out S3 from here, what am I left with?
S1, S2, the previous result.
So this is your result of division, which was same as the result we got here.
Yeah.
Is it clear to
And
everyone?
last part you explain again from where S3 after S3, how did you go?
We extracted S3 from here, right? From this pi of x minus y.
Yes.
So S3 comes out from here. Now there is a subtraction operation here, set difference.
Okay.
So that S3 has to be taken out from the first set that we evaluated. There is this one, SID, S1, S2, S3. So just take out S3 from here. We are left with S1 and S2. That's the result of the difference. Okay, everyone, is it clear?
Ma'am, I have a slid out in starting the question. Please go above.
Yeah.
Ma'am, here in division, why S3C1 is not come in course SID, EID?
Why S3 is not coming here in the answer?
Yes, yes.
Look, with S3, I have a combination with C1, correct?
Yes.
But I do not have a combination with C2. I need to have combinations with all possible values, right?
Okay, got it, ma'am. Thank you.
That's why S3 is not there. Okay, but this derivation will not be asked in exam. It's just so that you understand. I did it with this example. You don't have to memorize this. Okay. Maybe you can just take a look at this expression once in case it comes as an MCQ. That is, the expression is given and you are asked to identify which is the correct division expression. But that type of question is not asked usually. So I hope this is clear. So now we have done all of the operations in relational algebra. Okay, next we'll move on to relational calculus. Okay, before that, one question I would like to ask. One second. I'll not be discussing TRC from this slide, but just one thing. Okay, first tell me what is procedural language and what is non-procedural language. There are two types of languages, procedural and non-procedural. What does it mean? What are the differences between them?
Ma'am, I what I know is procedural language is like we define each and every aspect what the code has to run, and non-procedural is like predefined, and we give a few query type statements to get the data which we want to.
Yeah, that is pretty good. Okay, so basic, what you said is correct. Now, procedural language means what? Procedural language, the code is written as a sequence of instructions, right? In procedural languages. So the user themselves have to specify to the machine what to do and how to do, right? So both things we need to specify. Now these instructions will be executed in sequential order and they're written to solve specific problems. So these instructions solve specific problems. They must be executed in the same order as they're written in. And the user in a procedural language has to give both instructions on what to do and how to do. So example of such procedural languages like C, we had some older languages like Basic, Fortran. These are all procedural languages. Now what we use in DBMS is SQL, which is a non-procedural language. So in non-procedural language, user only has to tell the machine what to do, not how to do. Okay, how to do is not required. That is already known. So this type of language is also known as an applicative or a functional language. Okay, this will involve what? This involves the development of functions from other functions to create more, complex functions. So,
Ma'am,
for
I could not
example,
understand this. What is procedural and non-procedural? I can
we don't
visualize it.
we don't have to go into too much details in this. What we have to understand is procedural language is where user tells the computer what to do plus how to do. Okay, example, C programming language. Non-procedural is where the user tells the computer just what to do. So what you want done, nothing else.
Ma'am,
How to
when you
do
say
part
how to
is
do,
not.
do you mean the order of executing statements when you say how to do?
Yes, that and how the operations will be executed. So when
The
you
set
do
of
a select operation or a false join in SQL, you are not concerned with how it is being executed, right? That is not.
Okay.
Ma'am, is Python a procedural language or non-procedural language?
What do you think?
procedural, I think.
Why?
Because I am
We have
telling
to.
you what to do, how to do.
I think so
So
it's a mix of both.
Python is procedural, but mainly Python can be called as a separate class like object oriented language, right? It is procedural only. So you can write Python in procedural style, but we like Python itself falls under object oriented languages.
Don't you say it's a
See,
mix of both?
anything that
other than
supports
C, which is
functional.
old, other than C, which is old, give a recent example of a procedural language.
We don't work much with procedural languages now, right? So C, COBOL, Fortran, these were all procedural languages, which were used in the past. Now we use mainly object-oriented languages. See, whatever supports functional programming, right? That is procedural. So C, Java, Python, Java, these all support this function-oriented programming. So these are all procedural in a sense, but these are object-oriented. Okay.
Ma'am, so if we create a function in the procedural language, then can I call it non-procedural? Means after creating the function, the user is not directly instructing the machine
But
to.
you have defined the set of rules in the function, so
Yeah.
you
So
tell how to
whenever
do.
you are telling what to
In
do
the
and
same
how to
way,
do.
the select and join everything is predefined in the SQL
Yeah,
also.
it is all predefined. You don't have to
So
tell the computer
what
what to
is
do.
the
You just
difference
have.
between the Python function and this
So
select
in
and
this
all?
this first of all, Python code and SQL code you cannot compare because one of them is object oriented code and SQL code is just a query you are writing. It's a select from where query. There you are specifying what you want to fetch. Okay. In when you write an SQL code, do you have to tell the computer how to run that code? No. Right. You
Ma'am,
just have
that's
to
what
specify
I
what you want. So that's why
ma'am,
SQL becomes non-procedural. You just tell what to do.
ma'am, but the select function and every query is predefined.
Yes.
What the computer should do,
Hmm.
it is predefined. We are just using it as a function.
That's why it's non-procedural.
So is it not the same as the Python function?
So Python are all functions predefined. Can you not create new functions?
Yes, we can create.
We can create. And in Python, see, Python, that's why I was
Ma'am,
not willing to say
hello.
that it is a procedural language. Okay, it is an object-oriented language which we can write in a procedural manner. It is possible to do procedural programming with Python. Okay, Python will allow that structure. See, in
Ma'am,
a procedural
we can even
programming,
create, hello,
you
but
can
we can
create
even
functions
create
in
function
SQL
in
also. Yes,
SQL
I
also,
know.
yeah.
If you do the function trigger part, you will learn that you can write functions in SQL also. But see, it is not that simple. This thing goes a lot deeper. If you want to discuss it, this discussion will take a lot of time. That see, in I'll just tell in brief. In procedural programming, a program has to be organized into a sequence of instructions, right? Which can often be grouped into functions or routines to perform some specific tasks. So Python will allow this structure where you can define these functions and call them in a specific manner to achieve some outcome, right? While that is also the case in case of SQL, also you can define these functions, but SQL is not a procedural language. Here, you do not have to define to the computer exactly how to run these operations that you are asking it to run. Like if you do a left outer join, you are not having to tell it how to do that. In Python, we do not do these things, right? In Python, we don't have any such operators that we are using. Python operators are different. Those are already predefined. Those are in the library functions that you use. Right? Python is not very comparable to SQL. Okay, one is a scripting query language. This is a DML. SQL that we do is a DML. It is a data manipulation language. But Python is not that. In Python, you can also do DML tasks. You can manipulate data using Python, definitely.
And
But
one small question. I know it might go long, but I just when the lecture started, sir also told there's a tutoring language and a non-tutoring language. What does he mean by that?
What language?
Tutoring language or non-tutoring language, something like that.
It's a Turing complete language.
Oh, tuning complete. Yes.
Turing complete. Okay, yeah. No, that thing is impossible to discuss now because if you're not familiar with what are Turing machines. Okay, so there is a concept of Turing machine. So if you ever take a course on theory of computation, automata, finite machines, like FSMs, then you will be able to understand what is a Turing complete language, what is non-Turing compatible. All of these things. I mean, this is a whole other discussion on theory of computation that I cannot go into here.
Just 2 lines, you just tell me a brief what Turing
No, it's
machine.
not possible. See, Turing machine is a whole different concept. For that, you have to understand what is an automata. That has a whole different set of rules. Right? Turing machine is a theoretical model of computation. That's all I can say. It's a model of computation, and it uses a lot of things like tapes, read write head, set of rules, symbols. These are all part of TOC. So that course in future, if you ever get to take, then you'll understand what is a Turing acceptable language, what is not. Okay. All right. So yeah, for now, procedural, non-procedural, just knowing this much is enough. Procedural is both things you have to tell. Non-procedural is you just tell what to do. Example is SQL. Now let's move quickly to our this thing, TRC, DRC. What is actually going to come in exams? This is visible, right?
Yes, sir.
Mm, one second. Yeah. So first we will discuss tuple relational calculus. These are also non-procedural. Okay. So this is also non-procedural query language where each query is of this format. Now we'll discuss this format. What is T, what is P, all of these things. So what is T? T is the resulting set of tuples. And this P is nothing but the predicate. So like in selection, we wrote like this, where P was the conditional predicate, right? Same thing, that same condition P is now here. So this, how will we pronounce this notation that T is a set of tuples such that the predicate P is true for this set. So P of T is known as predicate, and these are the conditions that are used to fetch the set of tuples T that you want in your result. Okay. Now, there are various combinations that you can do in this predicate. You can join one or more combinations of conditions using or variable and or operator and operator, not operator. So it also uses something called quantifiers. So there is something called an existential quantifier and a universal quantifier. So this inverted E, this is your existential quantifier. Means if I write like this symbol is read as there exists. So this notation, see, there exists a tuple T which belongs to relation R. This is belongs to symbol, which belongs to relation R such that this Q predicate is true for this set of tuples. So that means there exist some tuples in this relation for which the Q or the predicate is true. Not all tuples in the relation, right? So if in a relation I have, let's say I have a relation for students, I have 10 students in that relation. Now my tuple is that I want students whose age is greater than 12. Now there are students of various ages, so only a few tuples will be accepting that condition where the age is greater than 12. So for them I can write that there exists a set of tuples that belong to the relation student where this condition age greater than 12 is true. So for this type of cases where not all rows correspond to the predicate condition, you can use there exists quantifier. But if I want all rows, right? So if I want, let's say, some predicate that is true for all tuples in a relation, then I will use the for all symbol, that is this inverted A. So for all tuples that belong to the relation R, the predicate Q is true. So two types of quantifiers we'll be using. Now, this is a TRC query. So here you can see now not always we are going to use TR like this. Okay, we can use any variable we want as the quantifier. So here I have written P. P is what? The resultant set of tuples. Okay. Better way to say this. 1 second. So in this, tell me what is the predicate? The table is the students table, which has some name attribute, some age attribute, some CGPA attribute. So what is the condition that you can see right away? That CGPA has to be
CGPA greater than 8
greater
and
than.
name.
Okay. Now these things, why we use these? These are not conditions. So basically this query, what it symbolizes is that for each student S in students table, see there exists S belonging to students. This means for each student S in students table with CGPA greater than 8, we will create a tuple P that includes their name and age. Understood? The quantifier here is S, which represents every tuple in the students table. So S belongs to students. There exist, that means there are some tuples at least in S. There are some tuples S in students where the CGPA is greater than 8, and for those tuples we are going to have a resultant tuple P which will include just their name and age. So this name and age is nothing but the projection operation. Okay.
Ma'am, I am not getting.
Okay, I'll say it again. See. First part of TRC query, this P. This is what? Resultant set of tuples. That is the ones that we desire to get out of this query. Resultant set of tuples. This straight line, this is such that. This means such that. That means I want a resultant set of tuples such that. Where are these tuples coming from? There exists a tuple S belonging to the student relation where the CGPA for that tuple is greater than 8 and we want to extract the name and age of that student. So whatever we want to extract, whatever we want to project, whatever we want to show in our result, the attributes, they have to be written in this format. That in P, the set of tuples that I want to show in my resultant table, right? In my result table. What are the attributes I want in my result table? I want name and I want age, right? So this
Ma'am.
P is nothing but coming from an actual tuple in the student relation. So that actual tuple is represented by S. That means for every S that is present in student relation, every row that is present in student relation, wherever I see that CGPA is greater than 8, I will extract the name and age of that student and present it as a tuple in my result.
Ma'am, when you say S dot CGPA, generally when we talk about some variable dot CGPA, we're referring to the table's column, no, ma'am?
But
So
here this is
how?
not the case. This is calculus. Here the representations are different.
So
Here S
what
is
is?
not a relation. Here S is a quantifier.
Is it a tuple or a quantifier? I'm confused, ma'am, a bit.
So see, okay, I will show you this. What is a quantifier?
Ma'am,
In
it's like a
predicate,
reference point, right? Sorry
yeah,
for
it's like a
interrupting.
reference. Correct.
It's not in the
Correct.
table. Like in SQL, it used to be in the
See,
table
S
where
is not a particular tuple. It refers to all the tuples one by one. Okay, and we will have to compare the condition CGPA greater than 8 for all tuples, right? And then we can extract the name and age for each of the students
Ma'am,
that match the
so
criteria.
in this case, you kept using the word for all. Isn't that the
For
inverted
no,
A?
no,
Why are we
this is
using there?
there exist. This is there exist, not
So
for all. This symbol is
so
there exist.
okay. Ma'am, when will
Ma'am,
we use there exists and when will we use for all in relational?
That's what I explained in the beginning, right? For there exist means what? That there are at least some tuples in student relation which for whom the condition is true. And for all when I use means that for all tuples in student relation the condition CGPA greater than 8 is true. Right? But here I don't know that for all tuples is it true or not. So I am assuming that there are at least some tuples for whom this is true. If such tuples exist, then I will fetch the name and age of those students.
So, ma'am, S is a quantifier here.
S
It
is
is
a
not a
quantifier. It is not a
okay.
table. So
So
in
there
predicate
exists
logic,
S.
like, in predicate logic, what are quantifiers? Predicates are used alongside quantifiers. What is my predicate in the question I was doing? That CGPA greater than 8. This is part of your predicate. Now, what are quantifiers doing? So using quantifiers, we create the propositions. That is called quantification. Means see, in predicate logic, predicates are used alongside quantifiers to express the extent to which a predicate is true over a range of elements. Means in my student table, there is a CGPA column, there is a name column, there is an age column. So some student might have CGPA 7, some might have 8, some might have 9, some might have 10, and their corresponding name and ages are there. So what are they saying? That we use quantifiers alongside predicates to express the extent to which a predicate is true. What is my predicate? CGPA greater than 8. So is this predicate true for all tuples in this relation?
No, ma'am.
That table will filter, ma'am. 8, 9, and 10 will be the predicate, right?
No,
Only
9,
9
10.
and 10. It is
Greater
greater
than,
than 8.
okay. 9 and table, the table which will get from this,
So
uh,
this
that will
is
be the
doing
predicate.
what? See, this means what? That only this part of the
That
table.
will be
This
filter from
so,
the filter
okay.
taken out from that
For
table.
only this part of the table, the predicate is true. That means there
Yes.
exist some
Yes.
tuples for whom the predicate is true. That's why
And
you are
for that,
using
name
the
and age will come.
yes. For that we are using the
So
existential quantifier.
what if we use for all over here? What would happen?
For all is not holding true over here. For all already means that for all tuples it is the condition is true. But here that is not the case. So for all will be wrong to use here. For
ma'am,
Okay,
all
ma'am.
that is the question here. Actually, what is the use of this universal quantifier? It has to be correct
I'll
for
show
all
you.
or wrong
I'll
for
show you.
all.
Isn't it better if I show you with an example, right? So that's why
Yes, ma'am.
let's first
Please,
discuss
please.
this.
Yes, ma'am.
Then I'll go to for
We'll
all.
go ahead with an example.
Yeah.
Ma'am, when you say there exists S, that means you're trying
That
to
means there
connect
exists
there
a tuple.
exists. You're trying to connect there exists to S. So
Yes.
wherever we see S, it's going to be there. There should at least be one.
Like S is what? S is the quantifier variable. Okay. So
Okay, ma'am.
there exists S is similar to saying there exists a tuple. In so belongs to students means in relation students where this predicate is true. That is the CGPA greater than 8 is true.
So, ma'am, the
But,
predicate should
ma'am,
be in the brackets.
Yes, predicate part is
The
in the brackets.
brackets. Got it.
But ma'am, that predicate need not be true. It may come
Yeah,
out
it
with
might not be
empty
true
empty
for
table,
all of
right?
them. Yes,
It
that's
may
why
come
this is
out with the empty
existential.
rows. Oh,
Look, for existential quantifier, if I take the first row here the predicate is wrong. 7 is not greater than 8. So for that tuple, so that means what? This current S tuple that I'm dealing with, here the predicate is not true. So it will not be a part of my result. So I will not fetch the name and age. I'll only fetch when all conditions are true. Okay.
So, ma'am, quantifier is the further condition. If we have
Quantifier is used to create the proposition. Okay, this is predicate logic. Means what? Here you will have two things. You will have the predicate and you will have the quantifier. So quantifier is something that shows that, okay, existential means there are certain tuples in the relation which will be for whom the predicate is going to be true. Universal means for every tuple the predicate is going to be true. Quantifier is just a variable. Okay, you can think of it as a deference to the tuples.
Ma'am, if we use for all and we give some predicate, then it would select based on the predicate, right? What is the use for using for
Look,
all or
take this
exist?
example. If I say, so for all is universal quantification, right? Means that in mathematical statement, if I say, so in mathematical statement, sometimes we assert that a property is true for all values of a variable in a particular domain. So that is the domain of discourse. So if you take a universal quantification in this sense, let's do it. So let Px, this is the predicate, right? Let Px be the statement that x plus 2 is greater than x. So can you say that this statement is always going to be true for any value of x?
Yes.
Yes.
No,
Right?
ma'am. No, ma'am.
If x is a real
If it's
number,
negative.
Okay.
if x is a real number, then can I say this statement is true for all x?
Yes.
Yes, ma'am.
Yes.
So what is the truth value of this predicate? For all x, p of x. This
It
is
is
always
correct.
true.
True. Always true.
So that's the thing. As solution, you can
This
say
is
that as
natural number, ma'am.
any real number. If you add 2 to any real number.
Yes, ma'am.
Like -5.
Ma'am, what is the use
So
of
negative
such?
5 plus 2
Negative
is
3
what?
is
Negative 3, which is greater than negative 5.
yes.
Right? These
Ma'am,
things
what
you
are the
can
use of such
Yes,
statements?
ma'am.
These are always true. Means what is the use of this universal quantifier? We all know this kind of truth, like sun rises in the east.
Okay. See. How can I put this? Quantifiers,
Ma'am,
why
don't take
we
that much of pressure. No problem.
see, this is much easier to understand if you have done discrete mathematics and you have done the predicate logic part. I know most of you haven't. So in DBMS, why we need it is in some queries. Remember, there are queries where we do select start, right? So we're selecting everything. We don't care about the predicate. We don't have any condition, or I can say select uh, some attribute name, and then I can in the where clause I can give some condition. So you have to learn to draw parallels between SQL and this relational calculus, just like we did parallels between SQL and relational algebra. See, if I write a SQL query, I need to write that exact query. I need to make sure that exact query can also be written in the form of algebra and calculus. Okay. Without quantifiers in calculus, you cannot write that. For example, why I took this example, this is very easy to understand that if x is a real number, then this predicate will always be true for all x. So in predicate logic, we ask such questions that a predicate will be given to you, obviously not nothing such simple as this. Okay, if you do discrete math in gate level, if you are planning to do gate CS, if you're planning to give that exam, then you will have to study that part of predicate logic in discrete mathematics. There you will see that there are very complicated predicates for which you will have to find out whether an existential quantifier is the way to go or a universal quantifier, right? Here it is very easy to see that, yeah, definitely universal quantifier if x is real number. But in all cases, it won't be very easy to discern. Why am I showing this? This is to see that how quantifiers itself work. Now, if I do an existential quantifier, let's take this. X is any real number. And I'm saying that my predicate is x is greater than 5. So what is the truth value of the statement that there exists x, px? Means there exists some x for which px is true. Is this a true statement?
Yes, ma'am. True.
Yes.
Yes.
1, 2, 3, 4. For these x values, 0. For all of them, this is true. But for x, 6, 7, This statement is not true. That means not for all x values. So the quantifier is there
Ma'am,
exists.
for 6, 7, it will be true, no, ma'am?
I'm sorry, for 6, 7 it is true, 1, 2, 3, 4 it is false. Right, so x has to be greater than 5. That's the condition. So that means for not all x values the condition is true, but for some values it is true. So there exists is the correct quantifier for this situation. So
So,
in
ma'am,
maths,
ma'am, in simple words, predicate is just a condition,
condition. It is just a condition.
and quantifier is to emphasize that condition.
Quantifier is what? To
Uh,
check for a particular, in our case in DBMS, for a particular table, we have to check that are all tuples following a condition, or is there
it
an
is
existence of
for
at least some tuples?
further
So it is to
constraints.
check that. It is to check that predicate. Okay. Always you have to use a
Can
quantifier along
quantifier
with your
be
predicate.
can quantifier be the predicate and predicate
No, no, no.
be the
Predicate is
quantifier?
a completely different thing. You cannot mix these two
Can you
things.
go
See,
to
some
that
things. Okay. First, let me
blind?
clear something. Okay. In when we write calculus statements, when you did it in your +2, there are some notations. We cannot question everything why this is happening. This is a notation. I didn't invent it. Somebody invented it, right? So it is to follow certain rules. This is predicate logic from which we derive relational calculus. So if I write there exists x of px, this is a mathematical notation. This means that there exists x, some values of x for which px is true, where px is a predicate. Right? I cannot say that I want to write there exists px of x. No, that is not possible. You cannot just invalidate statements, right? You have to follow certain rules. These are just a set of rules that you have to write, the notations that you have to learn. Now, if you let me, I will show you some actual examples in DBMS where this type of question is asked. Okay, I think that will be better. If you want,
Ma'am,
you can
here,
just go through that 4.2
ma'am,
lecture and then, yeah.
in this example, uh, s dot cgpa is greater than 8,
Hmm.
and p dot name is equal to s dot name,
Hmm.
and p dot age is s dot age. We can write these three conditions in any order, no?
Yeah, any order.
So here, why the CGPA is greater than 8 is predicate, and
This whole
mm,
thing is predicate. Inside the parenthesis, whatever is there is the predicate. Predicate is the condition, and in this case, in TRC, it is also fetching what are the attributes that I will fetch in case the predicate is true, in case the condition is true. This entire thing makes up the predicate inside the parenthesis.
okay. So what is the quantifier here?
Existential quantifier. Here, there exists S. S is your quantifier variable.
Ma'am, but P also should be a quantifier, no, ma'am? But there is no there
P is not a
exists of for all.
quantifier. P is not a quantifier.
Then
P
what
is
is?
just a tuple variable. That these are the
Okay.
tuples that I want to fetch. So P is
Okay.
written in the front. That P is this resultant set of tuples. How am I
And
getting P? Wherever S condition, this condition is satisfied.
okay, ma'am, could you explain what would happen if it was for all S over here?
So for all
As
S will
just
not work here because we don't know, right? This will not give a true value. This will give a false value if I use a for all S. So this will automatically mean what? That there are all tuples in student's table. This condition is true. That's
okay,
not the
ma'am.
correct thing.
So, for example, if there was a for all S belongs to students where S dot CGPA is not null,
Yeah, that is
then
true. That is a true
then
value.
then
If
what will we get
CGPA,
as the result?
no, see, result is what you fetch like this. Here I fetch that p dot name is equal to s dot name, p dot age is equal to h dot age. This is what you are fetching, the name and the age. Okay, that
Okay,
will be
ma'am.
showed in your result. The predicate that you're saying that CGPA is not null. So if this predicate is valid, when will this be valid? While you're creating the students table, if you had mentioned that the CGPA attribute has to be not null, in that case, this
Yes,
will
ma'am.
be a true value.
Okay,
Okay.
ma'am.
Otherwise, you cannot say for sure.
So, ma'am, this what I understood is this whole statement is being evaluated to true or false.
Yes.
But in general, when we are talking about relational algebra, we are getting a set of tables. Sorry, a set
Look,
of rows, no,
true
ma'am.
or false is evaluated from this part mainly. Okay. P is the result. So for every tuple for which this part returns a true value, that tuple will be in the result.
Got it, ma'am. Got it.
Okay.
Thank you, ma'am.
So
Thank
for
you for
every
explaining.
such event.
So
Yes.
p dot name and p dot is what it is representing.
That means in the resultant tuple, this name and age of this particular student for whom the CGPA is greater than 8 will be reflected. Only the name and age will be fetched. So whatever attributes you want to fetch, you have to write it like this. What did I say? See, listen to this statement carefully. For each student S in students table with CGPA greater than 8, we have to create a tuple P that includes their name and age. Understood?
So these are two tables, and we have to select the match the names.
These are not two tables. You did not listen to me carefully. What did I say? For each student S in students table, there is only one table called students.
So we are renaming. We are
We are creating a tuple P which includes their name and age if the CGPA is greater than 8.
No, so p dot name is equal to s dot name. So here we are.
This is notation. This is notation. This is how to write it.
Okay. Yes. We are naming the same table, no, madam. The p dot name is equal to s dot name. So we are in the same table. We are naming the
You
table.
are not renaming. I don't. Okay.
Okay.
See, I will try to explain it one more time. P and this p dot name is equal to s dot name, and p dot age is equal to s dot age. These things are what you are trying to fetch in case the condition matches. From the students table only you are trying to fetch. This forms a tuple P in your result. Got it?
Oh, okay. Yes. Yes. Yes.
Excuse me, ma'am.
Yes. Yeah, are you asking something?
Yeah, ma'am.
Okay.
I was saying like we are selecting name and age from student table where this condition is like say GPA is greater than 8, right?
Yes.
Ma'am,
Just
if there are
that.
no records, ma'am, if there are no records at all, which is greater than 8, so it will return null, right?
Then it will
Nothing.
not return anything. Yeah, null.
Yeah, that's acceptable result, right?
Yes, definitely.
Okay.
There are some SQL queries which don't return a result, right?
Yeah,
Because
sure.
there is no such
Because
data in the table.
the reason I'm asking is the notation itself there exists. That means an assumption that something is already existing
Yeah,
there.
we are doing an assumption only. These are all
So
assumptions.
if there's
It can
nothing
always
there,
give a
then it
false
will
value. Yeah.
false value. Okay, thanks.
Okay, now the similar notation we'll do for DRC. See, DRC notation is easier to understand. Not a lot of things here. So this is the predicate part. Okay, first, this is better for you since you had problem with that part, that why we are writing p dot name is equal to s dot name. Here we don't do all of that.
What is DRC, madam?
Domain relational calculus. Okay, previous was tuple relational, this is domain relational. So here what we do, we rename the columns of the table. So for example, take this table, name, age, marks, subject. When I want to write a DRC query on it, I will have to pick domain variables for each of the columns. So I can name them as A, B, C, D. The domain variables are always going to be in the same order. So take this query, for example. So what I want to find is name and age of students having marks above 75. Tell me the select from where query for this. Select. What is the SQL
Name,
query for
age.
this?
Select
Name,
name
age
from
Age
students.
student.
from
Where
students. Where marks is greater than 75. Now we have to write this in DRC format. Where what did I say? We will be using domain variables for each of the columns. Okay. So we have 4 columns: name, age, marks, subject. How many domain variables will need? 4. So there exists A, B, C, D. Now the order is same as the order in the table. That means A corresponds to name, B corresponds to age, C corresponds to marks, and D corresponds to subject. If I wanted to write X, Y, Z, W, then X corresponds to name, Y corresponds to age, Z corresponds to marks, W corresponds to subject. Order does not change. Fine. So there exist these 4 domain variables. Where do they belong from? They belong from students relation. And what is my condition? So this whole part is your predicate. Okay, this whole part after such that is your predicate. This is the quantifier, this is your predicate. What is the condition? That marks is greater than 75. Now which domain variable corresponds to marks? C. So C greater than 75. This is your predicate. Now what do I want to return? Name and age. Which domain variables correspond to name and age?
A and B.
So A and B in the result. So first you write A and B such that there exists ABCD where ABCD belongs from students and C greater than 75. So DRC is much easier than TRC for some people to understand, right?
Yeah, this is much easier actually. Much,
This
much.
is easier. But TRC is also easy. I mean, once you start practicing, you'll get it. I mean, it's not very difficult. Just the quantifier part, you have to understand that here also it holds true. I mean, quantifier you have to do in both cases. But there was that extra part that you have to write that equality, right? That P dot name is equal to S dot name. So whatever you want to fetch, an equality you have to correspondingly write. The more you treat this as notation, the easier it will become.
Ma'am, here the quantifiers are A, B, C, and D.
Yes.
Because
Four
thereafter
domain
there
variables.
exists.
Yes.
Okay.
So these are, we are going to call them as domain variables, right? This is the quantifier, existential quantifier. These are the domain variables. So there exists ABCD, where this ABCD belongs from students relation. So if there is one more column here, you have to add one more domain variable E for that column, right? So as many
it's like-
columns, that many domain variables.
So if you have 10 or more than any number, all the numbers have to be reflected.
That's
So
why I
it's
said that
too-
even though DRC is easier to write, it is not
Too
very.
cumbersome.
Yes,
See,
TRC is the
Cannot keep
better
right.
choice.
Notations are quite difficult.
What?
So,
Ma'am, what AB is?
AB corresponds to which columns? Name and age.
Ma'am,
Domain variables. A, B, C, D are all domain variables. This first AB is what we want to return in our query, name and age. So here we don't use the name of the actual columns, we use the domain variables. Okay. So all the important thing here is to remember that you have to mention domain variables in the same order as given in the table.
Ma'am, if there are more than one table?
No, we will perform it on one table only for now, right? We haven't even learned this properly, so I won't go for two tables currently. Let's do for one table first.
Ma'am, so
There can
DRC.
be two tables. See, this example itself is based on two tables, right? We'll learn how to do it. Yeah.
Ma'am, DRC and TRC, why it is two type of query?
Both, see, one is based on tuples, one is based on domain. Okay, but both are similar in power. So whatever you can write using TRC, you can also write using DRC.
No,
There is no functional
what
difference
DRC
between
is
the two.
doing here in this example? What DRC is doing, what that TRC cannot do?
Whatever DRC is doing, TRC can do the same. You can write this same query in form of TRC also.
Ma'am, so
Tell
any
me.
query in
Basic
SQL
difference.
can be written in relational
Any
algebra,
query,
DRC,
yes.
and TRC.
Yes,
Any
and
query.
relational algebra, SQL, TRC, DRC, all of them are functionally equivalent.
Got
Ma'am,
it.
my query is why it is different. Means what is difference between the two?
We have domain variables here, A, B, and C,
See,
D.
here you have the domain variables. There you don't have that. That's why you have to mention all of
What
the
is
actual column names.
what is domain variable means?
So that's what I said in the beginning, right? A, B, C, D, these are all domain variables. Means these are all the corresponding variables to each of the column in the actual table.
Column
For
names.
every column, you are going to have to take a domain variable. So this now, from once you have given the domain variables, from now on you have to address each of the columns as a domain variable only. You cannot use the column names. Okay. But the order must remain same. See, as long as you don't solve some questions, it will never get clear. So let's do this question first. So now you have two relations, student and activity. So write down RA, TRC, DRC. There is relational algebra, two types of calculus. All three expressions will write, which will return the names of students whose age is greater than 25 or who are enrolled in maths. So like I said, predicate can always join more than one condition using and or clause. This is and operation, this is or operation. So what we want is names of students whose age is greater than 25 or who are enrolled in maths. Okay, so this is from the students table. So what will be the relational algebra? That's very simple. First we do the selection operation. The selection age has to be greater than 25
Yes,
or
or symbol.
subject has to be maths.
Yes.
So any one of these. Now all the tuples are gathered from these conditions. Now you have to project what? Name. Just the name attribute. So projection of name. So relational algebra is the simplest one. Now corresponding TRC, how will you write? First, let's write the set of tuples that is T. This is the resultant set of tuples. There is an existential quantifier because not all tuples will have these conditions, right? So we are saying that we will fetch a set of tuples T if there exists S belongs to students, where S is a tuple of students, where the S dot age attribute is greater than 25, subject S dot subject is maths, and what do we want to return? Name. So T dot name has to be equal to S dot name. This is just to fetch the desired attribute in our result, and this is the conditions.
Ma'am,
This is
so
the
what
clear.
we have to return should be corresponding with the outside, like T dot
Yes, yes.
name should be returned. That's why we are including only T dot name equal to S dot name. And since age is not asked, it's just in the where part, so we are not including that T dot
Exactly. That
age,
means,
etc. etc.
what does this part mean? That the tuple T that is in my result, the T dot name attribute in that tuple should be equal to the S dot name for an S for which these conditions are true. That's all. You are just fetching the name of a particular student.
Yes, yes.
Okay. Now,
Ma'am, can we directly write T and then this bar and there exists T belongs to student and then
don't
T
use
dot
same
age
variables.
is
You cannot use same variables. This is the quantifier variable. This is the set of tuples. Okay, they have to be separate. And now DRC will be what?
Ma'am, there in DRC after there exists, there's no A. But in the previous
Yeah.
example, they
So,
were all A, B, and C.
yes. So ideally, when you write DRC, always write all variables. Okay, but it is okay if you don't write it as long as you mention it here. Okay, this is mandatory that you have to write all of this here. This quantifier part is not mandatory for all variables. Why? Because see, A that is not mentioned here. Is there any condition that is there on the A attribute that we have to?
Ma'am, a small query. I feel why they skipped A, because since before you said it should not be like T should not be as S. That's why like A should not be in A, B, C, D.
Yeah,
Where
that is one reason. Another thing that I'm telling, that is one thing, right? But this is different than TRC. This T and S and this relationship is different. This is a tuple variable, this is a quantifier variable. But these are domain variables. And this is what the variable, the domain variable for whom I want to return the values. Okay, these are all domain variables only. But
tuple variable, domain variable, and quantifier variable means I understand you are naming them, but what is actually meaning? They are meaning the same thing only.
no, they're not the same thing. That is what I tried to explain this whole time, right? That quantifier is trying to check the predicate, whether it's a true value or a false value. The tuple variable is, it is referencing all of the tuples that are in your resultant relation. And a domain variable is what? The domain variables correspond to all the different columns in a table, in a DRC query.
Ma'am?
The domain variables don't exist in TRC. Yeah.
Can we say that TRC is a row-based operation and DRC is the column-based operation?
Can say that. Column based, yeah, you can say that. Yeah, there is nothing wrong in it. Because you're saying that because here mostly we are using the domain variables to extract the columns directly. Yes. Yeah, I can say that. But in both cases, we have to work with each individual row, right? Now,
and
why
ma'am,
this is
in TRC, last condition, why we need to match the T dot name is equal to S dot name?
This shows you what you are fetching in T.
Because we have already filtered the age greater than 25
Yeah, that is fine. But have you
is
anywhere mentioned that
already
you want
there
to
in
fetch
T dot
name?
name.
Yeah, where is
Age
it
greater
given?
than 25 is already filtered all the rows
Hmm.
from the main table student. So why we need to
This is
again
just
match them?
filtering. This is just filtering.
Ma'am,
This is just the
ma'am,
selection operation. Where
ma'am,
is
this
the
is
projection operation?
ma'am, this is the same as we are making the this the cross product of two cross product of table, and then we are matching the identical.
No, 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 no. It's not at all like that. See,
No, this same concept is used in the cross product of tables. That's
no, 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 no. These are not same thing. This part, why it is necessary? T dot name is equal to S dot name, right? This S dot age greater than 25, S dot subject equals to math. This is the condition. This is the filtering. But have you anywhere stated that what I want in my result? I don't want all columns in my result. I just
No,
want the name column.
that I am understanding that we need the names, right?
Hmm.
But from a table of suppose 10 rows, we have
Hmm.
filtered 5 rows which contains all the names same. So
Hmm.
why this logic is there to T dot name is equal to S dot name? How it will give the output in respect of the name that I'm not getting?
Wait, you're saying that in a table all the names are same?
No, in the table, uh, we have filtered from the condition that T dot name greater than 25, right?
T dot age
And
greater than S dot age greater than 25.
age is greater than, okay.
Yes. We have filtered based on age and subject. So now we have those rows, the
Okay, okay.
desired rows
Now,
I
now,
have.
now I understand. That is a temporary T
That's your
which
selection
is
operation.
filtered. Okay, okay, fine.
Yeah. S is a reference to every single tuple that we are checking.
Ma'am,
Yeah,
is there any
that is a temporary table, right?
Yeah,
And from
it
that
just
temporary table,
quantifies.
we are comparing the original ones and
Hmm.
filtering, right?
Yes.
ma'am,
S
is there
is
any
going through
relevance
every
second
tuple in the.
line?
Yeah, sorry.
Second line in the TRC.
Yeah, this is another way of writing TRC. If you want me to discuss it, I will discuss it because I am not discussing because I feel like you're confused enough. So I don't want to do this
Yes,
right.
ma'am, that's better.
Okay. Maybe in the next class, when you have had a chance to solve more questions, then you can ask the instructor to just discuss this part once. This is
No,
nothing
I'm
but,
asking, is it the
same
both
thing.
lines are combined or different?
No, no, different. These are different ways of writing the TRC query.
Uh,
Okay. Here
ma'am,
we are not
actually,
using a quantifier.
instead of quantifier, we directly like at the
Yeah.
end statement, we are like outside only we are mentioning T dot name, so we need not use that
Hmm.
quantifier, right?
Yeah,
Okay.
that's all we are doing. Just skipping the quantifier. But for now, forget about this. Just work with the quantifiers. Okay. DRC. So here, why we are not using the A and why that is fine is because where are the conditions? See, the conditions are on B and D attribute, right? Also in C, there is no condition. So even if I remove C from here, that is also fine. But B and D must be there because based on these two domain variables, I have the conditions. This is notation. Best way you write all four. Okay. See, this is where I'm defining that A, B, C, D are the corresponding columns of students table. This is the quantifier variable and this is based on which I will check the predicate. So here, if you have only B and D, this will also work for this particular problem since the condition is there only on the B attribute and the D attribute. But better you write all four here to avoid confusion. Okay. And what do I want to fetch? I want to fetch the name. So only the domain variable A is there. So domain variable A, where B is greater than 25, B means age, and D is equal to maths, D is subject. This is this same query written in all three formats, RA, TRC, DRC. Now I'll quickly do one more example, this one. Activity. Now we are doing based on both tables, students and activity. Okay. So RA, TRC, DRC expressions which will return the names of students along with sports whose age is less than 25 and who have secured more than 75 marks. Okay. So age has to be less than 25 and marks has to be more than 75. And we also need the sports. So firstly, tell me what are the things I need to project in my result? Name and
Sports.
Sports.
That means I have to join the two tables. Okay. I don't know if you have studied natural join yet. Have you done join types
Yes,
of
ma'am.
join?
Yes,
Yes,
yes, ma'am.
Yes, ma'am, we did it, ma'am.
Types of join is done, right? So this is natural join symbol. So can I do natural join on student and activity?
Yes.
Yes.
Yes, ma'am.
Yes.
Based
Ma'am,
on what?
on name attribute, right?
Name.
Based
Yeah.
on name attribute.
Name is the same.
Okay. So by that I can just do a natural join. Now
Ma'am, a small, sorry for disturbing. If there are more than two, then what to
it
do
will
over
take
there?
both. Natural join will take both together. You don't get to specify. However many common attributes are there, it will take them all together and use the combination.
Then we should go for the inner join. No?
There is no necessity. That depends on the query itself. Okay. If the query can be done using a natural join, do it regardless of how many common attributes are there. In this case, like you can easily do a natural join, or you can do an inner join also. It will give the same result.
Ma'am, another, if we do natural join, it would take any one of the
No,
common.
it will take all common attributes.
Ma'am, that's not the definition of natural join, right? It
Natural
would take
join,
only one
no.
attribute, right?
Natural join takes all common attributes between two tables. Inner join, you can specify one attribute that you want, one common attribute. Natural join by default takes all common attributes, whether it is one, whether it is more than one.
Ma'am, natural join matches the common attribute, right? If there are more than two common attributes, then it will
Then it
return
will
a
match both.
empty table.
No. That's not
Ma'am,
how natural join works. Natural
Piyush
join
sir
will take
has defined that way actually.
what has he said?
Am I
Exactly.
right, everyone? Could you just support if I'm wrong or right?
I think he has told that result will vary. It will make a combination of all the joins,
No,
all the commons.
ma'am, I will study. Listen. Suppose there is ID. ID is given a common in both the table. Then ID will be given only one.
Actually, he said in a particular database, natural join won't work because the names, the values are not same. Like
No.
names are
See,
same.
what he meant is natural join will occur, but it will not fetch any value if there are no matching combinations.
Exactly.
Yeah.
Okay, but it will
Yes, ma'am.
check the matching combinations always. Natural join by default will check all possible combinations of all common attributes between the two tables. But
Yes.
it might be the case that there is a null set. There are no
Yes.
matches. That might
But
be.
suppose there are two tables and I want to make a join on one particular column and there are two commons.
Then
So
you do an
I should
inner join.
be inner join and I should
You
to be
can
on safer
specify.
side.
Yeah, you can
Okay, and
specify
specify
based
that
on
column. That was the
because
point.
natural join will by default take both.
Otherwise, if I want on my requirement and it will join on both the common points.
So if you're already know what the data is, if there is going to be matching combinations, then you can use natural join. It is safer to use an inner join in that case. Okay, now here, since there is only one common attribute, I can easily do a natural join. So what are my conditions? Age is greater than 25. So sigma of age less than 25 and marks greater than 75. This is being selected from where? From the natural join of students and activity. Okay, and then what do I need to project? The name and the sports. So just projection of those two. Same thing if you want to write in TRC. Now we have two tables, so I need two quantifiers. So this is set of tuples T, resultant set of tuples. So there exists S belongs to students and A belongs to activity. So S dot name is equal to A dot name. This is to do the natural join. I am doing the join here. That is, I will look for only those tuples this name matches in both tables, like David matches with David here. And S dot age is less than 25. Right? So what is the quantifier variable for students table? S. So S dot age less than 25, S dot marks greater than 75. What do I need to fetch? Name and sports. So T dot name can come from either of the tables. I can do T dot name is equal to S dot name also. I can do T dot name is equal to this A dot name also. Activity also has the same column. They have used S dot name. And sports has to come from activity table. So T dot sports is equal to A dot sports. Similar DRC query. Now again, you have to have couple pairs of domain variables. So first domain variables are what? A, B, C, D for students table, and then E, G, E, F, G, H for activity table. So this is E, F, G, H. So A, B, C, D belongs to students table. On which attributes do I have my this thing condition? Age. This is B, and C, that is marks. So B has to be less than 25, C has to be greater than 25. This part is done for the first student table, right? And another condition is there, which is we have to also fetch the ports. So all the domain variables for activity table, and we have to perform the natural join. So you can only perform the natural join after both domain variables have been declared. So now A and E are both declared, so you write and A equals to E. That means this name equals to this name. So this is the natural join part. And what you are fetching is A and F. A is name from students table and F is ports from activity table. You can also fetch this E and F also, because this is the same name. Is this clear?
Yes, ma'am.
Ma'am, could you just explain the TRC one again?
TRC, I need now two
No,
quantifiers.
not TRC, ma'am. DRC, the last
Okay, DRC. Now I need two sets of domain variables, each for one of the tables. So I took ABCD for students table and I took EFGH for activity table. Right? Now, where are the conditions? I can place the conditions in students table in attribute B and C. Age has to be less than 25, so B less than 25, and marks has to be greater than 75, so C greater than 75. And in the activity table, do I need to fetch anything from that in my result? F, ports, right? So what am I fetching? A, comma F, that is name and sports. But I have to perform the natural join also, right? This natural join. I have to join the two tables. So that natural join is being performed here. A is equal to E. Why is it being performed here? Why not beforehand? Why can I not perform it here? Because till now there is no existence of E. E has been declared here. Once E has been declared, then you can perform the join, right? But
Got
how
it.
this query will execute? First it will do the join, then it will pose all of these conditions, then it will fetch the actual data.
If there is any condition on the activity table, then we have to
Then you can
mention
just
it in
add
the
an
EFG.
and of
Ma'am, in TRC.
and
Yeah, okay.
Ma'am, in TRC, how to use T?
Hello,
How to
ma'am.
use what?
Hello.
Ma'am, here T dot name and T dot sport.
Yeah, so you have written that here, right? T dot name is equal to S dot name, T dot sports is equal to A dot sports. So these are the two things you are fetching in your result.
And ma'am, okay.
Just take some time to look at the queries, okay? Before you ask any questions, just sit silently and look at the query. It will all make sense. Everything is accounted for.
Yes, ma'am.
Don't you think we can go through discrete mathematics course for better understanding?
Sure, you can go through it, but it's see, discrete mathematics is not just predicate logic. It's a huge course, okay? There is group theory, there is a lot
Yeah,
of other things. So if you want, you can check out
right.
the
Because
predicate
the
logic part.
professor was saying one in the starting,
Yeah, I know.
and
It is a
I
good
also
field.
started it. I am
No, we can
in
repeat
a,
this lecture now.
Yeah, you can repeat this lecture. It is on YouTube. You can also check the previous term lectures. Okay, all of this is there. If you still want to learn predicate logic, plenty of videos are there on YouTube. NPTEL videos are also there. So you can check that also if that makes the quantifier thing more clearer to you.
Okay.
Ma'am, in DRC, how it is clear that what B means what, A means what in
So
the
that's
student?
what is given in the beginning, that whenever you write domain variables, the order is same. ABCD is same order as name, age, mark, subject.
But you
A will
don't have
always correspond
no
to
order
name.
of attributes in a relation.
That is the rule of DRC, that the order in which you declare the variables is the order in which it will take as the corresponding attribute name. If I write BCAD, then B will be name.
Where are we declaring the?
This is the declaration. ABCD belongs to students.
But we have written it in name, age, mark, subject. But there are no order.
This is the order. This will take by default.
Already given in the order.
If you take ABCD, then A will always correspond to the first column, B will correspond to the second column. If I write XYZW, X corresponds to name, Y corresponds to age. Right? Whatever is in the table, that exact order is preserved in the domain variables. Okay, just take some time and go through this lecture again if you need to. This will take some getting used to, right? TRC, DRC is the tough part to understand.
Yes.
Now the rest of this week is very easy, only ER diagram is remaining. We'll cover that on Saturday.
Ma'am,
Yeah.
I have a doubt in this TRC bar activity, right? There exists S from a student.
Sir,
There
1 second.
exists.
Ma'am, is the lecture over?
Yeah, it is over. You can leave.
Okay.
Thank you, ma'am.
Yeah, thank you.
Ma'am, there exists, in respect of TRC I'm talking, there exists S belongs to a student. There exists A belong to activity, right?
Yes.
And S dot name is equal to A dot name, right? It is doing natural join,
This
cross
is the
join.
join. Yeah. No, this is natural join.
Okay.
Okay, this part, first part is the join. Then you place the conditions.
And age is coming from S dot age and
Yeah. Since here, why we can do it in the beginning? Because we have already declared the quantifier variables S and A. But here I am declaring E later on. That's why the join happens at the end.
okay, thanks.
All right. Yeah. Okay. Thank you, everyone. Thanks for joining, and
Ma'am,
also
thank you
join the
for explaining.
Saturday
Thank you.
session. Yeah. Thanks.
Thank you, ma'am.
Thank you, ma'am.